All right, so 3-2 is about conditional probability. Today we're mostly going to talk about the multiplication rule. First couple things you don't have to write down. We'll get to the problems that you see on there in a second. So they mentioned this in the law of large numbers video about independent events. Independent events are when you have successive events, one's probability does not affect the other. So the example they give here is tossing a coin and rolling a die. If whatever happens with the coin, it does not affect what happens with the dice. Okay. So an example of how probabilities could differ if I have independent events versus dependent events. And a lot of times, specific wording in the problem is going to tell you that you have independent or dependent events. And they use the words replacement and not replacement, or not replacing as you go. So here we have a bag of marbles. You can see there's, let's see, 4 white, 2 that are black, one that's crossed out there is black, and then a couple that are black and white. We want to find the probability of pulling a black marble 2 times in a row. So the probability notation would look something like this, the probability of black and then black. When we see or hear or can interpret the word and, it's going to be multiplication. That's going to be the multiplication rule we're going to see in a second. If we have independent events, that would be like after my first pull, putting the marble back in. That's with replacement. So the probability of drawing a black marble would be 2 out of 10. I put that black marble back in the bag. So on the second trial, it's also 2 out of 10. And then if I multiply those together, I get a 1 out of 25 probability. If they are dependent events, after I pull that black marble out the first time, I leave it out. So it's still a 2 out of 10 chance for that first black marble to be drawn. But when I leave that marble out, the second probability that I'm going to multiply changes. And in this case, both the numerator and the denominator change. There's only 1 black marble left in the bag. There's only 9 marbles left total. So I end up doing 2 out of 10 or 1 out of 5 times 1 out of 9, and that would give me a 1 out of 45 chance. So the probability is a lot smaller because of the dependent situation, because I did not replace. Okay, so the first thing that we're going to do on your paper is we're just going to label these situations as either independent or dependent. If the probability of one or one thing happening affects the probability of the other, we're going to say they are dependent. If one does not affect the other, independent. All right, so first one, selecting a king from a standard deck of playing cards, not replacing it, and then selecting a queen. Is that dependent or independent? They are dependent events because I did not replace. Good. Tossing a coin, getting ahead, and then rolling a 6-sided die and getting a 6. Dependent or independent? They are independent. One does not affect the other. Driving over 85 miles per hour and then getting in a car accident. Would one happening affect the probability of the other? Yes. Okay, doesn't mean it's for certain going to happen, but the faster you drive, the higher the probability that you're going to get in an accident. So because that probability changes, we label it as dependent. All right, smoking a pack of cigarettes per day and developing emphysema. Independent or dependent? Do you think one affects the other? Dependent. Okay. Tossing a coin and getting a head. Tossing a coin again and getting a tail. Independent. Okay. Any questions on independent, dependent? No. Okay. On your purple packet, you will see these 2 formulas. The first one, I would read it, the probability of A and B, and again, we're going to remember that when we see and, it means multiply. That's why we call this the multiplication rule. I would read it, it is the probability of event A happening times the probability of event B given that A has already occurred. And that's what it looks like if it's dependent. This is pretty much just saying this second probability isn't just the probability of B. B has changed a little bit because A has affected it. Okay? That's what it looks like if it's dependent. If it's independent, you're going to see it looks exactly the same, but we don't have that little given A at the end. Honestly, I don't really remember this one. I just remember this one, and then I know, hey, if I've got dependent events, that second probability is going to be a little bit different, like the marble rule, or the marble example that we saw. Okay? So you'll see both of those on your purple sheet. They're labeled dependent and independent. They're both under multiplication rule. So what we're going to do now on your paper, I think, is practice with that multiplication rule. Okay, so for ACL reconstructive surgery, the probability that a surgery is successful is 0.95. First thing we're going to do is find the probability that 3 surgeries are successful. So that means the first one is successful, and the second one is successful, and the third one is successful. When we hear the word and, we're thinking multiply. So we're just going to take the probability that each is successful, which is 0.95, and we don't have anything here to tell us that one affects the other in any way. If it did affect the other, we have no probability that we'd even be able to calculate that with anyway. So the fact that they don't give us any other information says, hey, these are pretty much independent events. Multiply those together, 0.95 pretty much to the third power. Maybe if my calculator wants to work, there we go. I get about 0.857. Okay. Find the probability that none of the surgeries are successful. Okay, so that means the first one is unsuccessful, the second one is unsuccessful, and the third one is unsuccessful. If the probability of success is 95%, what's the probability of failure? Right, it's a complement, right? 1 minus the probability that we have. 0.05, 0.05, 0.05. Okay. So 0.05 to the third gives me 1.25 times 10 to the negative fourth. I'm just going to write it all the way out. This is what that number looks like if I write it in standard notation. Okay. The third one is where things are going to start to get tricky now. Find the probability that at least one of the 3 surgeries is successful. Okay. So there's a lot of different ways this can happen. Either the first is successful and the next 2 are failures, or the middle one is successful only, or the third one is successful only. Okay, so that's a way for one of them to be successful. Or 2 of them could be successful. So the first and the second, or the second and the third, or the first and the third. Or all 3 of them could be successful, which that's one we already calculated. That was the 0.857. Okay, so this is all the different ways in 3 trials and 3 surgeries that at least one, so 1 or 2 or all of them are successful. Could I calculate each of these probabilities? Sure, because success is 0.95 and failure is 0.05, and I can multiply them all together. And if I wanted to do this problem, I would then just add all of those probabilities up. I don't want to do that though. This is going to take a while, and you can imagine if we made this problem 5 surgeries or 6 surgeries or 7 surgeries, all the different combinations that I could possibly have here. It would be a little crazy to do by hand. So there's a little note at the bottom of this page on your paper. See if I can make mine appear. It says the probability of at least one occurrence of an event is the complement, 1 minus the probability of none. So here's what I would write on there. It rhymes. It's easy to remember. The probability of at least one is the complement of none. At least one is the complement of none. At least one thing happening is everything except none of them being successful, right? In this case. Okay, so at least one is the complement of none. So in this problem, get my pen back here, at least one is what I'm calculating, is the complement 1 minus the probability of none of them being successful. And conveniently, we just calculated the probability that none of them were successful. So if I do 1 minus the probability of none, what I'm left with is all those other possibilities that we listed out if I had calculated those probabilities independently and added them all up. So if I do 1 minus that number, I get 0.999875. Exactly. Could round it if you needed to. So it's almost certain that at least one of the surgeries will be successful based on these probabilities. Okay. Any questions on that problem? At least one, the complement of none. All right, flip it over to the back. Let's do a few more probabilities. So some of these were those situations we labeled as dependent, independent. So remember, we're multiplying the probabilities together. You just need to think about, does one probability affect the other, or are they independent of each other? Okay, so 2 cards are selected without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. Okay, so probability of selecting a king would be what? 4 out of 52. Okay, and then I just have to think about, in the second probability, if I do not replace without replacement, what's going to change here? Okay, so I take a king out. How many cards are left in the deck? And then I'm calculating here the probability of selecting a queen. How many queens are left in the deck? Still 4. And then that's what we multiply together. 4 out of 52 times 4 out of 51, 0.006 approximately. A coin is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. What's the probability of getting a head? And rolling a 6 on my die. So 1 out of 12, or 0.083. Okay, probability that it's a mouthful, salmon swims successfully through a dam is 0.85. Find the probability that 2 salmon swim successfully through the dam. So based on what we're given here, do you think these are independent or dependent? Just salmon getting through. If one salmon gets through, does it affect the probability of another one getting through? If it did, we wouldn't be able to calculate it because we don't know how the probabilities would change. So we're assuming that they're independent here. So this is kind of like the ACL problem. One of them has an 85% chance. The other one has an 85% chance. Multiply them together, 0.7225. 2 cards are selected from a deck of 52 playing cards without replacement. Find the probability that they are both hearts. Okay, so what's the probability that the first card selected would be a heart? 13 out of 52. Okay, it's 13 of each suit. If I pull out a heart and I take that heart out, how many hearts are left? And how many cards total are left? 51. All right, so 13 out of 52 times 12 out of 51, I get 0.059 approximately. Okay, any questions on those? Multiplication rule. Okay, last slide, and this might come up in the 3-1 homework, I think somebody told me. So we talked about unusual events with standard deviation in the last chapter. If a data value was more than 2 standard deviations from the mean, it was considered unusual. Probabilities are considered unusual if they are less than 5%, so below 0.05. If they're greater than 5%, they're not considered unusual. Unusual and unlikely are words that we use kind of interchangeably here. All right, in a jury selection pool, 65% of the people are female. Of these 65%, 1 out of 4 works in the healthcare field. Find the probability that a randomly selected person from the jury pool is female and works in the healthcare field. Is it unusual? Okay, so the probability that the person selected is female is 0.65. And the probability that they work in the healthcare field is 1 out of 4. 0.25. Multiply them together. I get 0.1625. Is the event unusual? Is that probability unusual? No, it's not less than 5%. Okay, find the probability that a randomly selected female or person is female and does not work in the health field. Okay, so again, probability that they're female, 0.65. Does not work in the health field, we're thinking complement now. If we see the word not, so the complement of 0.25 is 0.75, which that's going to give me something that's bigger. 0.4875. Is it unusual? Is it unlikely? Nope. All right, and then that's all we're going to do with 3-2 today. So tonight, you need to make sure you finish up your 3-1 Math Excel. Tomorrow, we're going to finish up 3-2 in class, and then your 3-2 Math Excel is due on Friday night. Those are your 2 assignments this week, okay? All right. I'll do cell phone.